there is a quiet assumption buried in the phrase, the biggest planet. It sounds like a claim about size and nothing more, as if Jupiter was simply Earth with the volume turned up, the same kind of object scaled to a larger setting. Hold that assumption in mind, because it is about to crack. Start with one number. If you took every other world in the solar system, Mercury, Venus, Mars, Saturn, Uranus, Neptune, every moon, every asteroid, every comet nucleus, and gathered them into a single body, Jupiter would still outweigh that body by about 2.5 times. It carries roughly 318 times the mass of Earth, and something on the order of 1,300 Earths would fit inside its volume. And here is the first crack in the assumption. Jupiter does not hold that mass in a neat sphere. It is visibly out of round, wider across the equator than from pole to pole, squashed enough to notice in a backyard telescope. That is not what a scaled-up Earth looks like. Over the next 2 hours, we are going to follow a single thread, from that mass to the planet's internal heat, its record-breaking spin, its enormous magnetic field, and its centuries-old storms, and see whether biggest and most violent are 2 facts about Jupiter, or 1 fact described twice. If that is the kind of question you like to sit with, consider subscribing, settle in, and let's begin. Return to the mass, because it is not a trophy, it is a load. 318 Earths of material all pull toward the same center, and that pull never relents. Every layer of Jupiter is pressed by the weight of everything above it, and near the core, the pressure climbs to millions of times the pressure of Earth's atmosphere at sea level, with temperatures rising into the tens of thousands of degrees. Nothing about that arrangement is static. The interior is hot because it is compressed. It is compressed because the planet is heavy, and the heat is constantly trying to leak outward towards space. This is the setting for everything that follows. When we talk later about heat welling up from inside, about hydrogen behaving like a liquid metal, about a magnetic field that dwarfs the planet it comes from, each of those is a response to this same inward squeeze. Jupiter is, before anything else, a structure holding itself up against its own gravity, and the unrelenting effort of doing that is where its power comes from. It helps to be precise about what biggest means, because it is not mainly about width. Saturn is nearly as wide across as Jupiter, yet it has less than 1/3 of Jupiter's mass. It is puffy and light. Jupiter is the biggest planet in the sense that matters here, which is mass, the amount of material, and therefore the amount of gravity. Hold that distinction, because almost everything in this video turns on mass rather than diameter. Now look again at the shape. Jupiter's equatorial radius is larger than its polar radius by about 7%, a difference of roughly 4,600 kilometers. On a body more than 11 times the width of Earth, that is a bulge you can see. Point a modest telescope at Jupiter on a steady night, and the disk is not a circle. It is a slightly flattened oval, noticeably wider than it is tall. A rocky planet like Earth cannot deform that way. Jupiter can, because it has no solid surface to resist, and because it is spinning fast enough to throw its own equator outward. The shape is the first visible fingerprint of motion. That motion is extreme. Jupiter completes one rotation in under 10 hours, close to 9 hours and 56 minutes, which makes it the fastest spinning planet in the solar system, despite being by far the largest. A point on its equator is carried around at about 12.5 kilometers every second. Earth's equator, by comparison, moves at less than 0.5 kilometer per second, slow enough that we never feel it. Jupiter is more than 11 times wider than Earth, and it still whips around in under half an Earth day, which means its equator is traveling more than 25 times faster than ours. So the largest planet is also the one turning most quickly, and it is turning quickly enough to visibly reshape itself. Size and speed are already tangled together, and we have not yet left the surface. Put those pieces side by side, and a pattern starts to form. The oval disk is not a curiosity. It is mass and rotation writing themselves onto the planet's outline. This is the reason the opening assumption fails. Jupiter is not a large planet doing ordinary planetary things on a bigger stage. It is a body whose mass and spin have pushed it into a different regime, where the familiar rules of a world, a firm surface, weather driven by sunlight, storms that come and go, begin to bend. The rest of this video is about what happens once they bend. If size forces the shape, the next question is what else size forces. It is worth pausing on what 318 Earth masses means as a force rather than as a figure. Mass on its own is just an amount of material. What matters for Jupiter is that all of that material generates gravity, and that gravity pulls inward from every direction at once, toward a single center. The planet is not resting easily at its size, it is being compressed by itself. Everywhere, all the time, each layer bears the weight of every layer above it, and by the time you reach the deep interior, the pressure has climbed to millions of times the air pressure at Earth's sea level, with temperatures to match. The only thing preventing the whole structure from shrinking further is the outward push of that hot, compressed interior. Hold on to this image, because every violent feature we describe later, the heat rising from within, the hydrogen that behaves like a liquid metal, the field that reaches past several of its moons, is a response to this same inward squeeze. Before Jupiter is anything else, it is a body straining to hold its own shape against its own gravity. And that strain is where its power originates. A natural thought at this point is that Jupiter came close to being something far more dramatic, a star, and simply missed. It is a popular idea, and it is worth dismantling now, so it does not quietly distort the rest of the story. To sustain the hydrogen fusion that powers the Sun, an object needs somewhere around 75 to 80 times the mass of Jupiter. Even the far gentler deuterium fusion that flickers inside the smallest brown dwarfs, the dim, not quite stars, requires roughly 13 Jupiter masses. Jupiter has exactly one. It did not fall short by a sliver. It falls short by a factor of dozens, and no plausible history would have gotten it across that line. There is a genuine reversal buried in those thresholds. You might assume that if you kept pouring mass onto Jupiter, it would keep getting bigger. It would not. A cold sphere of hydrogen and helium near Jupiter's mass is already close to the largest that such a body is physically allowed to be. Add more material, and the extra gravity presses down harder on everything already there, so the planet grows denser and hotter without growing much wider. Astronomers see this in other star systems, where planets several times Jupiter's mass turn out to be barely larger than Jupiter across. Our planet sits near a size ceiling built into its own composition. So where does the inward pull go? If it cannot start fusion and cannot force the planet to expand, it goes into a standoff. The weight of the outer envelope is balanced by the pressure of the hot interior pushing back, and maintaining that balance is not free. The interior stays hot, in large part because it is being compressed, and it slowly bleeds that heat outward over billions of years. There is no solid floor anywhere in Jupiter for the weight to rest on. The planet supports itself entirely by pressure, the way the deep ocean holds up the water above it, except that here the column is tens of thousands of kilometers tall. Put simply, the work of resisting its own gravity is what keeps Jupiter warm from the inside. We will unpack the mechanism in the next chapter. But the essential point is that the mass is not a passive quantity sitting on a scale. It is doing something to the planet every second of every year. This is the thesis to carry forward. Jupiter is the largest object its recipe can build, and it is holding that size under permanent strain. The band from about 13 to 80 Jupiter masses belongs to the brown dwarfs, objects massive enough to fuse a little deuterium for a while, but never enough to shine steadily like a true star. Below that band sits Jupiter, not as a failed attempt at something grander, but as the fully realized maximum of something else, a planet. That distinction matters for the rest of this video. We are not going to describe a near star that almost caught fire. We are going to describe a planet pushed to the physical limit of what a planet can be, and then trace how that limit expresses itself as heat, as wind, as magnetism, and as centuries-long storms. Everything the title calls violence takes place under the load we have just described, and it happens precisely because that load never lets up. Jupiter's day is the shortest of any planet in the solar system. It turns once on its axis in a little under 10 hours, close to 9 hours and 56 minutes, so a complete Jovian day and night would fit comfortably inside a single work shift. For an object more than 11 times the width of Earth, that pace is hard to overstate. Because the planet is so wide, a point on its equator has to travel an enormous distance to complete each turn, and it does so at roughly 12.5 kilometres every second. Stand on Earth's equator, and you are being carried along at less than half a kilometre per second, slow enough that you never sense it. Widen the planet 11-fold, spin it in under 10 hours instead of 24, and that gentle drift becomes a genuine physical force. From here on, rotation is not a piece of trivia about Jupiter. It is one of the main things acting on it. The clearest evidence of that force is the planet's shape, which we have already noticed from the outside. Rapid rotation flings material outward most strongly at the equator, where the spin carries it fastest. Earth resists this because it has a solid crust that can hold a fixed form against the strain. Jupiter has no surface anywhere. It is fluid from the cloud tops down through tens of thousands of kilometers, so it does the only thing a spinning fluid can do, which is bulge. The bulk of the 7% gap between Jupiter's equatorial and polar radii, that visible flattening of the disk, is centrifugal stretching. Interior structure and deep winds add smaller adjustments. But the headline cause is plain. Spin a fluid planet fast enough and it flattens. Look more carefully, and the rotation turns out not to be a single, uniform motion. The visible atmosphere near the equator circulates in about 9 hours and 50 minutes. Regions at higher latitudes take closer to 9 hours and 55 minutes to come around. A difference of roughly 5 minutes per rotation sounds trivial, and in absolute terms it is small. Its consequences are not. It means Jupiter's atmosphere does not turn as one rigid shell. The equatorial belt is perpetually running ahead of the mid-latitudes, lapping them turn after turn for as long as anyone has watched. That endless slippage is what draws the stripes. Wherever a faster stream of atmosphere runs alongside a slower one, the boundary between them gets sheared, and the flow naturally organizes itself into long currents running east and west, rather than tumbling in every direction at once. Those currents are the belts and zones, the alternating tan and pale bands that make Jupiter instantly recognizable in any photograph. The darker belts are regions where the atmosphere is generally sinking, the brighter zones where it is generally rising, and the sharp lines between them are fast, narrow jet streams running in alternating directions. They are not a pattern painted onto a globe. They are the direct visible signature of a fluid planet spinning quickly and unevenly, combed out into ribbons by its own differential rotation. The thesis for this chapter is that rotation gives Jupiter a grain, a strongly preferred direction along which things are allowed to move. Nearly everything that flows on or inside the planet is steered east or west by that spin. The jet streams we will follow thousands of kilometers beneath the clouds, the currents in the deep metallic layer that generate the magnetic field, even the vast structure of trapped plasma that surrounds the whole planet. Rotation this fast also stiffens the flow in a particular way, making it organize into broad, stable, planet-circling bands instead of the messy swirls a slow rotator would produce. For contrast, consider Venus, which takes 243 Earth days to turn once and is very nearly a perfect sphere with no banding whatsoever. The single variable that separates the two is spin. On Jupiter, it is fast enough to leave marks visible from Earth through a small telescope. And the next question is how far below the clouds those marks actually reach. From Earth, through a backyard telescope, Jupiter's bands look like markings on a painted ball. The intuitive reading is that they must be shallow, a thin film of colored cloud stretched over an interior that is something else entirely, in the same way Earth's weather is a delicate skin draped over rock and ocean. For most of the 20th century, that was the working picture. And it was a reasonable one. We had nothing to test it against. One of the central questions the Juno spacecraft was built to answer was exactly how deep the visible circulation reaches. Are the stripes a surface finish, or are they the top of a structure that runs into the planet? Juno could not take a photograph of the interior, so it did something less obvious. It weighed it. Each time the spacecraft dropped in close to the cloud tops, its speed was nudged by tiny amounts, and the size of each nudge depended on how mass was arranged in the planet directly beneath it. By tracking those minute accelerations over many orbits, mission scientists reconstructed Jupiter's gravity field in extraordinary detail. Departures from a smooth, featureless field carry the fingerprint of how material is distributed under the clouds. And crucially, that includes the mass carried by moving air. The verdict on the jet streams was clear. They are not shallow. They extend downward to roughly 3,000 kilometers before they weaken and fade. 3,000 kilometers is hard to feel as a raw number, so anchor it two ways. On Earth, all of our weather, every storm, every jet stream, every cloud is confined to the troposphere, a layer only about 10 to 12 kilometers thick. Jupiter's active circulation is something like 300 times deeper than that. Put the other way, 3,000 kilometers is farther than the distance from London to well past Moscow, and it is a genuine fraction of the way from Jupiter's cloud tops down toward the level where hydrogen begins to take on metallic behavior. And the material moving through that depth is not a few streaks of haze skating over the top. The jets carry a noticeable fraction of 1% of the entire mass of the planet. On a body of Jupiter's size, that works out to several Earths' worth of atmosphere in continuous motion. What we casually call Jupiter's weather is a deep, massive, heavy circulation, not a cosmetic layer. That depth forces a conclusion about energy. A circulation that reaches thousands of kilometers down and moves that much mass cannot be powered by sunlight warming the cloud tops. The sun's light at Jupiter's distance is far too weak for the job, and in any case, it only touches the outermost skin of the atmosphere. It never reaches the depths where the jets are strongest. Friction, meanwhile, never stops. Layers of fluid, moving at different speeds, rub against one another and against the deeper interior, and that drag steadily drains energy from the flow. To have kept running for billions of years, the circulation must be fed from somewhere at least as fast as friction bleeds it. Something has to be driving that flow from beneath, resupplying its energy without pause. Left to itself, with no power source, a circulation of that scale would have spun down and gone still a very long time ago. There is one direct check on all of this. In December 1995, NASA's Galileo mission dropped a small probe straight into Jupiter's atmosphere, the only time any spacecraft has sampled the planet from the inside. It fell for about 58 minutes, parachuting down through roughly the top 150 kilometers to a pressure around 20 times Earth's sea level air pressure, before the rising heat and pressure destroyed it. One of its clearest findings was about the wind. Rather than dying away below the clouds, the wind stayed strong, and if anything strengthened, all the way down to where the probe went silent. A shallow, sunlight-driven weather layer should have calmed with depth. This one did not, which is exactly what you would expect if the winds are rooted far below. So the opening phase of this story closes on a reframing. The storms and bands we can see from Earth are not the machine. They are the exhaust of a machine. Beneath them lies a circulation that runs deeper than any ocean on Earth and carries the weight of several planets' worth of air, and it demands a steady supply of energy to keep turning. On Earth, that supply is the Sun, 93 million miles away. On Jupiter, as the next chapters lay out, the supply is the planet itself, pushing heat outward from its own interior. Jupiter orbits at roughly 5 times Earth's distance from the Sunday. Because the intensity of sunlight falls off with the square of distance, each square meter of Jupiter's cloud tops catches only about 4% as much solar energy as the same square meter would receive at Earth. Work through the consequences, and a passive planet at that distance should be a cold, dim body, quietly re-radiating the little sunlight it manages to collect and doing nothing else. Jupiter refuses to behave that way. When you carefully measure the heat streaming off it in the infrared and set that against the sunlight landing on it, the planet is plainly running a surplus. It emits more energy than it absorbs, and it has been doing so for as long as we have been able to check. This measurement is neither new nor fragile. It was first made from the ground in the 1960s, refined by the Pioneer and Voyager flybys, and revisited with modern instruments, and the result has held every time. Jupiter radiates somewhere on the order of 1.5 to 2 times as much energy as it takes in from the Sunday. The figure most often quoted from the Voyager encounters is about 1 2/3. A more recent analysis argued that Jupiter actually absorbs less sunlight than earlier work had assumed, which pushes the internal contribution higher again. The exact ratio depends on quantities that are genuinely difficult to measure. Above all, the planet's precise reflectivity across every wavelength, so it is honest to carry it as a range rather than a single crisp number. The existence and the direction of the imbalance, however, are not in dispute. Sit with what that imbalance means. If Jupiter puts out something like 1 7/10 units of energy for every single unit it receives from sunlight, then well over half of all the heat leaving the planet was never solar to begin with. It is Jupiter's own heat, generated somewhere inside and working its way out through the atmosphere towards space. In the planet's total energy budget, the Sun is the junior partner. To a first approximation, Jupiter is a body that warms itself and happens also to be lit by a distant star. Jupiter is not unique in this. Saturn and Neptune also radiate noticeably more energy than they absorb from sunlight. So an internal heat surplus is a general trait of the giant planets, not a Jupiter quirk. What sets Jupiter apart is the absolute amount. Because it is the most massive of the giants by a wide margin, the total power welling out of its interior is the largest of any planet, and that is the first hint that the heat and the size are not two separate facts but one. The comparison also rules out some tidy alternative explanations. If the excess were, say, a chemical reaction or some slow release of a stored fuel, you would not expect to see the same signature scaled with mass across 3 very different planets. What scales with mass is gravity, and gravity is where the next chapter goes looking. Some texture on the temperatures, because the word glowing can suggest something hotter than the reality. This glow is not visible light, it is heat radiation. Infrared, the same band in which a warm rock radiates on a cold night. At the depth where the pressure matches Earth's air pressure at sea level, Jupiter's atmosphere sits at about 165 Kelvin, which is close to 100 degrees Celsius below the freezing point of water. Its effective temperature, the one figure that captures its total thermal output, is lower still, near 90 Kelvin. The air is roughly 90% hydrogen and 10% helium by molecule count, with faint traces of methane, ammonia, and water. By every human standard, the place is bitterly cold and thin-aired, and yet, measured against how little sunlight it receives, it is unmistakably warm, and warm from the inside. So the picture changes. Jupiter has an internal power supply. It is not a stored oddity, and it is not a measurement artifact. It is a sustained output, comparable in size to the entire solar input, welling up from inside the planet. That rearranges everything that comes after it, and it puts a sharp question in front of us. What is the internal source? What process could keep a world that formed 4.5 billion years ago warm enough, even today, to outshine the sunlight that manages to reach it? What could keep a planet warm for 4.5 billion years? On a rocky world like Earth, A large share of the internal heat comes from radioactive elements decaying slowly in the mantle and crust. Jupiter is built almost entirely of hydrogen and helium, with only a modest admixture of heavier material, so radioactive decay falls short of explaining what the planet radiates by orders of magnitude. If the heat is not solar, and it is not radioactive, that leaves gravity. And the scale of Jupiter's gravity is the one thing this video has already established beyond any doubt. The leading explanation carries the names of Kelvin and Helmholtz, the physicists who first worked it out for the Sun in the 19th century. Jupiter is gradually contracting under its own weight, the entire planet settling inward by a small amount over very long spans of time. When material moves inward, even at a crawl, its gravitational energy is converted into heat, in the same way that a falling weight warms whatever it lands on. Because Jupiter is so massive, the cumulative energy released by this slow, continuous settling is enormous, comfortably enough to supply most of the internal glow we measured in the last chapter. The planet radiates that heat into space faster than sunlight can replace it, and the contraction keeps refilling the reservoir from below. It is a furnace with no flame, run purely by weight. There is very likely a second contribution, and it has to be labelled plainly as a proposal rather than a settled fact. Deep inside Jupiter, helium may not remain evenly blended with hydrogen. Under a particular combination of crushing pressure and temperature, helium can condense into droplets that are denser than the fluid around them, and those droplets then sink toward the center, giving up energy as they form and fall, much as raindrops release heat when they condense out of humid air and descend. This helium rain is a well-motivated idea, supported by interior models and by a direct measurement. When the Galileo probe sampled Jupiter's upper atmosphere in 1995, it found slightly less helium than the Sun's composition would lead you to expect. The straightforward reading is that some helium has drained downward out of the layers we can reach. How large a share of the heat budget that process accounts for is still genuinely uncertain, and careful accounts treat it as an open contribution rather than a closed one. The rate of shrinkage involved is far too small to measure directly and is estimated only from models. The planet is contracting so slowly that the change over a human lifetime would be undetectable. What makes it matter is not the speed but the mass being moved. Multiply an almost imperceptible settling by 318 Earths, sustained over billions of years, and the total energy released is more than enough to run the glow we measured. Notice how neatly this loops back to the size ceiling from earlier. Jupiter cannot relieve the strain of its own gravity by lighting fusion, and it cannot relieve it by swelling outward, because adding mass would only compress it harder. So the pressure has nowhere to go except into this slow, self-limiting contraction, and the contraction is what generates the heat. The furnace and the load are not two systems. They are one system seen from two sides. The planet is warm because it is heavy, and it cannot stop being heavy. All it can do is settle, imperceptibly, essentially forever. The thesis of this chapter is that Jupiter's size is not merely associated with its heat, it is the fuel for it. The planet is still shedding energy left over from its own formation, cooling on a timescale far longer than the current age of the solar system. And that, internally made heat, has to escape. It rises through the deep hydrogen envelope on its way towards space. And rising heat in a fluid does not travel quietly. It does work on everything it passes through. The next chapter is about what that work produces when the rising heat meets a fluid thousands of kilometers deep on the fastest spinning planet we know. Bring the last 3 chapters into a single frame. Jupiter has a genuine internal heat source, powered by the slow contraction of its own enormous mass, releasing energy comparable to everything it receives from the Sunday. It has a fluid envelope that stays fluid for tens of thousands of kilometers, with a measured, active circulation reaching at least 3,000 kilometers down. And it has the fastest rotation of any planet, a full turn in under 10 hours. Taken one at a time, these are interesting facts about a planet. Taken together, they describe a machine. Picture a pot of liquid with a burner underneath, except the pot is deeper than any ocean, and the entire pot is spinning hard enough to flatten itself. There is no arrangement of those ingredients that sits quietly. Take the heat by itself first. When a fluid is warmed from below, the warmed material expands, grows less dense than its surroundings, and rises, while cooler, denser fluid sinks to take its place. That overturning is convection, the same motion you see in a heated pan of water just before it boils, or in a mug of coffee with cream stirred through it. Inside Jupiter, the warmth comes from the contracting interior, and it drives rising and sinking motion through the deep hydrogen envelope without pause. The planet is continuously turning its own insides over, ferrying heat from the depths up toward the cloud tops, which is the only place it can finally radiate to space. Because the heat source never shuts off, the overturning never completes. It just keeps going. Now add the spin, because it changes the shape of everything. On a slowly rotating body, convection can rise more or less straight up in simple cells. On a fast rotator like Jupiter, a moving column of fluid is deflected sideways as it goes, pushed by the same Coriolis effect that curls weather systems into spirals on Earth. Only here it is far more powerful relative to the flow. Under rotation this strong, the fluid tends to organize into tall columns aligned with the spin axis, each column moving as a coherent unit, so the weather is really the visible end of structures that reach deep into the planet. Rising and sinking motions get bent and stretched into these columns, and into currents that run overwhelmingly east and west rather than up and down. Those east-west currents are the jet streams, and the alternating bands they draw are not a film of weather lying on the planet. They are the visible cross-section of rotating convection that fills the deep interior. The Galileo probe gave a direct taste of this in 1995. As it fell, it clocked winds in the neighborhood of 640 kilometers per hour. And, crucially, those winds did not fade as the probe descended below the sunlit cloud layer. On a planet where the weather was just a thin, sun-warmed skin, the wind should have dropped away with depth. Instead, it held all the way down to the crushing pressures where the probe stopped transmitting. That single vertical profile, through one location, is a real measurement of an atmosphere being driven from below. Here is the reversal against everything the word weather normally implies. On Earth, weather is a thin skin, driven from outside by sunlight, and it is fundamentally temporary. A storm assembles when local conditions align. It runs for as long as those conditions hold, and it falls apart when they shift, which on Earth means days or at most a few weeks. Jupiter's circulation is driven from inside, runs through a fluid layer thousands of kilometers deep, and is stirred without rest by the fastest spin among the planets. It has no external trigger to wait on, and no local fuel supply to burn through. It cannot end the way a hurricane ends, because none of its energy is seasonal, regional, or borrowed from the Sunday. That is the peak of this chapter, and in a real sense, the hinge of the whole argument. Jupiter runs a permanent storm engine. The heat of its own unhurried collapse rises through a deep fluid, the rotation combs that rising heat into jets and vortices, and the product is a circulation that has been turning without a single interruption for longer than Earth has had a solid surface. What we are calling Jupiter's violence is not a run of bad episodes on an otherwise calm planet. It is the ordinary, steady output of this engine at idle. Everything still to come in this video. The magnetic field, the radiation belts, the storm that has outlived every astronomer who described it, is either a working part of that engine or a direct consequence of it running. An engine like the one we just built, a deep, spinning, convecting fluid, tends to do one more thing beyond moving heat around. If any part of that fluid can carry an electric current, then stirring it in a rotating pattern generates a magnetic field. Jupiter does this on a scale nothing else among the planets comes close to. Its magnetic field is the strongest of any planet in the solar system, and not by a little. Expressed as a magnetic moment, the single quantity that captures the overall strength of a planetary magnet Jupiter's is on the order of 20,000 times Earth's. Bring that down to the cloud tops. There, the magnetic field is roughly 20 times stronger than the field at Earth's surface. If you could somehow hold a compass at Jupiter's cloud tops and shield it from everything else, the needle would be gripped far more firmly than any compass has ever been held on Earth. But the field is not the same everywhere. Its strength at the cloud tops varies from place to place, from around 2 Gauss in the weakest regions to something like 20 Gauss in the strongest, depending on where the measurement is taken. Earth's surface field, for comparison, is well under a single Gauss anywhere you stand. When the Juno spacecraft arrived in orbit and began skimming just above the cloud tops, its magnetometer measured the field from closer than anything had before, pass after pass, gradually building a detailed map. It confirmed something the earlier, more distant flybys had only hinted at. Jupiter's field is not a clean, smooth, bar magnet shape. It is lumpy and irregular. There are concentrated patches where the field is unusually strong and other regions where it is surprisingly weak, including a pronounced weak zone not far from the equator and an intense, tightly bounded region in the northern hemisphere. The planet does not present one neat magnetic pole per hemisphere, the way a simple dipole would. The real pattern is more tangled than that. Juno also caught the field changing. Comparing its measurements with those from the Voyager and Pioneer flybys decades earlier, scientists found that parts of Jupiter's field had visibly drifted and shifted in the intervening years, a slow evolution known as secular variation. Earth's field does the same thing, which is why compass corrections have to be updated over time. But seeing it on Jupiter is direct evidence that the field is being generated by a fluid in motion right now, not frozen into something solid. The magnet is alive and running. That irregularity is itself a piece of evidence about where the field is generated. A smooth dipole field would point to a generator concentrated deep at the planet's center. A patchy, structured field like Jupiter's suggests that a significant part of the dynamo action takes place in a broad shell that is not enormously far below the surface, close enough that the structure of the flow there prints through to the outside. The shape of the field, in other words, is carrying specific information about the geometry of the layers producing it, information planetary scientists are still working through. The whole field is also tilted and off-center. Jupiter's magnetic axis is inclined by about 10 degrees to its rotation axis, and the effective source of the field is shifted away from the planet's exact center. That may sound like a minor bookkeeping detail, but it has a real consequence. The radiation environment around Jupiter is lopsided. The belts ride closer to the cloud tops on one side of the planet than on the other, so a spacecraft's exposure depends not only on how close it flies, but on which face of this crooked magnet it passes. Every trajectory designed for Jupiter has to reckon with a field that is at once the strongest among the planets and noticeably askew. All of which means the field is a direct readout of the interior, and big planet, big field is not a reading of it. We have to say what hydrogen actually becomes when it is subjected to the weight of 318 Earths, and how a planet spinning this fast turns that material into a generator. That is the next chapter, and it is where the magnetic field connects back, once again, to the single fact of Jupiter's mass. Ask what hydrogen does under the pressure at the heart of Jupiter, and the everyday picture stops being any use. On Earth, hydrogen is the lightest gas there is. Pairs of atoms drifting upward through the air, so light it escapes the planet entirely over time. A few thousand kilometers down inside Jupiter, the pressure climbs into the millions of Earth atmospheres, and hydrogen is forced into a condition it never takes on anywhere in nature, on our world. Under that kind of squeeze, the bonds holding hydrogen molecules together give way, and the electrons that had been tied to individual atoms are set loose to move freely through the whole body of material. Free-moving electrons are exactly what makes a metal conduct electricity, so hydrogen here becomes a dense, electrically conducting liquid, in effect a liquid metal. Jupiter holds an enormous inner region made of this metallic hydrogen, spanning a large fraction of its entire volume. It is not a thin lining or a small central nugget. It is the planet's dominant interior substance. A deep conducting ocean with no surface, no shore, and no bottom in any ordinary sense, grading smoothly into the denser material near the center. This is not just theory. In laboratories, physicists have briefly squeezed hydrogen to pressures comparable to Jupiter's interior, using shock waves and diamond anvils, and watched it turn from a transparent insulator into a shiny, reflective conductor. The exact pressure of that change is still being pinned down, but it is of order 1,000,000 times Earth's atmospheric pressure. Inside Jupiter, that level is reached a few thousand kilometers down, and then vastly exceeded, so the metallic region is not a thin boundary layer, but the bulk of the planet. Now set that conducting ocean moving. The internal heat we traced in earlier chapters drives convection through this metallic layer, the same rising and sinking overturning, carrying heat outward. Jupiter's fast rotation then twists those flows into organized, corkscrewing currents rather than simple vertical motion. When you move an electrical conductor through a structured, rotating pattern like that, you get a self-sustaining dynamo. The motion generates a magnetic field. The field pushes back on the moving fluid and shapes its flow, and the loop sustains itself for as long as heat keeps rising and the planet keeps turning. It is the same basic mechanism that generates Earth's magnetic field in its molten iron core, but operating on an incomparably larger volume of conducting fluid, which is a large part of why Jupiter's field so dwarfs our own. Here is the causal spine of the chapter. Jupiter's magnetic field is not a fortunate extra fitted to a large planet. Given this much mass, the interior pressure is high enough to metallize a huge quantity of hydrogen. Given the internal heat, that metallic ocean convects. Given the fast spin, the convection organizes into a dynamo. Each step follows from the one before it, and the first step is nothing more than how heavy Jupiter is. For an object assembled like this, a powerful magnetic field is very close to unavoidable. The lumpiness Juno mapped fits this picture too. If the dynamo runs partly in a broad shell rather than only deep at the center, the field it produces should be irregular, with strong and weak patches, which is exactly what the spacecraft found. Which is why size builds the magnet. A smaller planet of the same hydrogen-helium composition never reaches the pressure needed to metallize enough hydrogen, so it cannot run a dynamo on anything approaching this scale. Saturn, at under a third of Jupiter's mass, has a real but distinctly weaker and smoother field. The ice giants Uranus and Neptune generate weaker and far more chaotic fields from conducting layers of water and ammonia, not metallic hydrogen at all. Jupiter's field is the one that reflects a specific, extreme mass regime. And in the next chapter, we follow it outward to measure how much space it actually commands. A planetary magnetic field does not stop at the cloud tops. It extends far out into space, and it hollows out a region around the planet where the planet's own magnetism, rather than the sun's outflowing wind of charged particles, sets the rules. That region is the magnetosphere, and Jupiter's is the largest single structure in the solar system, apart from the sun's own extended atmosphere. On the side facing the sun, Jupiter's magnetosphere pushes the solar wind back to a distance of roughly 1 to 3 million kilometers from the planet. Stated in Jupiter's, that is dozens of planet widths of cleared space between Jupiter and the boundary where its magnetic control gives out. Compared with Earth, whose magnetosphere is squashed to a small fraction of that on its sunward side, Jupiter's is enormous both absolutely and in proportion to the planet inside it. On the night side, the magnetosphere is pulled out into a long tail that streams directly away from the sun, and that tail is extraordinary. When Voyager 2 was cruising between Jupiter and Saturn, it registered disturbances that were traced back to Jupiter's magnetotail brushing past it, hundreds of millions of kilometers downstream of the planet. In that direction, Jupiter's magnetic reach spans the gap to the next world out. NASA offers a way to picture the sunward portion. If Jupiter's magnetosphere glowed with visible light, it would appear in Earth's night sky about the size of the full moon, even though it sits at least 4 times farther from us than the sun does. We would look up and see a soft, luminous disk, wider than any planet ever appears through a telescope, and it would not be the planet at all. It would be the volume of space the planet governs. The scale is easier to grasp by comparison. Earth's magnetosphere, on its sunward side, is squashed to about 10 Earth radii. Jupiter's stands off the solar wind at something like 50 to 100 Jupiter radii, and Jupiter's radius is more than 11 times Earth's to begin with, so in absolute terms, the bubble is on the order of 100 times larger than Earth's. Every spacecraft that has traveled that far out has felt it. Pioneer, Voyager, Ulysses and Cassini all recorded the moment they crossed Jupiter's bow shock and entered the magnetosphere, sometimes crossing back and forth several times in a day as the boundary surged past them. This bubble is not a fixed shell. Its sunward boundary swells outward when the solar wind slackens and is pushed inward when the solar wind strengthens. So the whole structure breathes in and out over hours and days, and the boundary can move by tens of planet widths between a calm solar wind and a gusty one. Where the oncoming solar wind is abruptly slowed, tens of Jupiter radii upstream of the planet, a standing shock wave forms in the thin interplanetary gas, the same physics as the bow wave that stands in front of a moving boat, scaled up to interplanetary size. Everything downstream of that shock belongs to Jupiter. The thesis here is a shift in what we even mean by the planet. Jupiter, considered as a sphere of influence rather than a ball of gas, is not an object 11 times the width of Earth. It is a region of space larger than the Sun, trailing a tail that reaches to Saturn, all of it organized by a field generated in a hidden ocean of metallic hydrogen. And that region is very far from empty. In the next chapter, we look at what fills it, and at where an entire magnetosphere's worth of material comes from. A magnetosphere the size of Jupiter's has to be filled with something, and the solar wind on its own does not deliver nearly enough. Most planetary magnetospheres, Earth's included, are comparatively thin environments, populated by a trickle of particles leaking in from the Sun and drifting up from the planet's own upper atmosphere. Jupiter's is dense and heavy by comparison, loaded with far more plasma than the solar wind could ever supply, and the source of that extra material is one of its own moons. Io, the innermost of the 4 large Galilean moons, is the most volcanically active body in the solar system, with hundreds of active volcanoes and lava lakes and plumes rising hundreds of kilometers above its surface. The reason it is so active traces straight back to Jupiter's gravity. Io, Europa, and Ganymede are locked in a precise orbital rhythm. For every 1 orbit Ganymede completes, Europa completes 2, and Io completes 4, an arrangement called the Laplace resonance. Those repeating alignments keep tugging Io's orbit slightly out of round, and a slightly elliptical orbit means Jupiter's enormous tide flexes Io by a different amount at different points in each circuit. The moon is squeezed and released over and over, and that constant kneading generates so much internal friction that Io's interior is kept partly molten. This was actually predicted in 1979, just days before Voyager 1 flew past and photographed the first erupting volcano ever seen beyond Earth. Jupiter then strips the erupted material away almost as fast as Io can produce it. Averaged over time, roughly 1 ton of matter every second is pulled off Io and into the space around Jupiter. That is, in effect, a moon being slowly quarried by the planet it circles, using energy that Jupiter's own gravity keeps pumping into it. The stripped gas first forms a fainter neutral cloud along Io's orbit, then is ionized by sunlight and by collisions with particles already trapped in the field. Once ionized, it is caught by Jupiter's magnetism and organized into a donut-shaped ring of electrically charged gas that encircles the planet along Io's orbital path. This is the Io-plasma torus, a standing reservoir of plasma, topped up continuously by Io's volcanism and drained continuously as material migrates outward through the magnetosphere. It glows in ultraviolet light and, to the right instruments, is one of the brightest features of the entire Jovian system. a permanent ring of Io's exhaust lit up around its own planet. Then Jupiter's rotation takes charge of it. The magnetic field is locked to the fast-spinning planet, and it drags the trapped plasma around with it, compelling that plasma to circle Jupiter roughly once every 10 hours regardless of how far out it sits. Far from the planet, keeping up with that pace means moving at tens of kilometers per second. As the plasma is whipped around at those speeds, centrifugal force flings it outward, stretching the inner magnetosphere into a broad, flattened, spinning sheet known as the magnetodisk. That disk carries an electric current measured in millions of amperes, and the current itself reshapes the field far from the planet, inflating the magnetosphere well beyond what the planet's field alone would support. This is one reason Jupiter's magnetosphere is so much larger in proportion to the planet than Earth's. It is not just held open by the field, it is pumped up from inside by its own spinning plasma. So Jupiter's magnetosphere is not a still pond. It is a centrifuge. The planet's spin, handed off through the magnetic field, forces an entire moon's worth of stripped volcanic gas to co-rotate with Jupiter and accelerates it to tremendous speed. And that sets up the next problem without any further ingredients. Take charged particles, accelerate them like that, inside a magnetic field this strong, and a fraction of them will reach energies that make the space around Jupiter genuinely hazardous to anything we send there. Take the strongest magnetic field of any planet, fill it with plasma stripped from a volcanic moon, and spin the whole system around once every 10 hours. Charged particles caught inside do not drift gently. The rotating field, together with waves and disturbances rippling through the magnetosphere, acts on them like a set of accelerator rails, nudging them to slightly higher energy on each circuit. Over many circuits, a fraction of the electrons are driven to energies that carry them at a large fraction of the speed of light. And the ions along with them, those high-energy particles pile up into belts, donut-shaped zones of trapped radiation wrapped around the planet. In broad layout, they resemble Earth's Van Allen belts. But the resemblance ends at the numbers. Near Jupiter, the density of energetic electrons is far higher than anything found in near-Earth space. And each particle carries far more energy on average. This is the most intense, sustained radiation environment around any planet in the solar system. And it does not vary with the seasons or the solar cycle in any way that makes it safe. It is always on, because the field, the plasma source, and the spin that power it are all always on. You can detect these belts from Earth without leaving the ground. The trapped electrons, spiraling along the field lines at close to the speed of light, give off radio waves. And Jupiter has been a bright radio source in that band since the 1950s, before any spacecraft had been near it. Long before we had a photograph of the belts, radio telescopes had effectively mapped their glow. The particles also scour the surfaces of the inner moons. The trailing hemisphere of Europa, the side that plows into the co-rotating plasma, is chemically altered and darkened by the constant bombardment. So the radiation environment is not just a hazard to spacecraft, it is actively weathering worlds. We know how severe it is because we have flown hardware through it and recorded what happened. The first probes to pass Jupiter, Pioneer 10 and Pioneer 11 inches the 1970s, encountered radiation far beyond what their designers had anticipated, and some of their instruments were degraded or briefly driven haywire during the closest approach. The Galileo orbiter, which studied Jupiter and its moons for years, absorbed tens of kilorads of radiation on each pass through the core of the belts, even with its sensitive electronics tucked behind shielding. Across the full mission that accumulated to a dose several times what the spacecraft had been built to withstand, and the effects showed. Instruments developed noise and glitches, and several components degraded in ways that matched radiation damage rather than ordinary wear. The belts are also structured, not a single uniform shell. There are more and less intense regions, and the large moons carve gaps as they sweep along their orbits, absorbing particles that would otherwise be trapped there. Cross into the zone inside Io's orbit. and the electron flux climbs steeply. This is the region mission planners treat as genuinely off-limits for any extended stay. Put a figure on the fully exposed case and it turns stark. A spacecraft flying a comparable mission with no special radiation protection would take a total dose on the order of tens of millions of rads over its time at Jupiter. For a sense of scale, a whole-body dose to a person of just a few hundred rads is life-threatening. The space near Jupiter delivers that dose many times over, continuously, to anything that stays, so the belts are the spin made lethal. The rotation that generates the field, and the field that captures Io's plasma, together turn that plasma into a sterilizing blanket of near light-speed particles. It is not an add-on hazard. It is a direct, mechanical output of the engine we have been assembling piece by piece. And it is why sending anything to Jupiter is, before it is anything else, an exercise in surviving the radiation. That is the subject of the next chapter. The clearest way to feel how violent Jupiter's environment is to look at what it does to our machines, because there the damage is measured, logged, and dated. The Galileo orbiter is the case history. It reached Jupiter in 1995 and spent almost 8 years working its way around the system, and on the passes that carried it through the heart of the radiation belts, it absorbed tens of kilorads of radiation each time, despite having its most sensitive electronics deliberately buried behind shielding. Over the whole mission, the accumulated dose ran to several times the level Galileo had been designed to tolerate. The spacecraft aged visibly under it. Its camera and spectrometers began throwing errors, its data recorder developed faults, and its star tracker, the instrument it used to know which way it was pointing, was thrown off by energetic particles registering as false stars. Engineers spent years nursing a machine that Jupiter was steadily degrading from the outside in, writing software patches to work around failing parts and rationing the riskiest observations for the passes when the spacecraft could best afford the damage. When NASA designed Juno, the spacecraft that launched in 2011 and reached Jupiter on the 4th of July 2016, the radiation was treated as the central engineering problem, rather than a footnote. Juno's most vital electronics, its main computer and the boxes that run its instruments and power, sit inside a dedicated radiation vault, a roughly cubic enclosure with walls of titanium about a centimeter thick, weighing on the order of 200 kilograms. It is, in effect, a small armored room built into the middle of the spacecraft. The vault does not stop the radiation, but it cuts the dose reaching the critical parts by a large factor, buying years of operating life that an unshielded design would never get. Even with it, Juno was originally planned for a relatively short campaign of close passes. That it has kept working long enough to enter an extended mission, adding flybys of Ganymede, Europa, and Io, is partly a matter of the shielding and the orbit performing better than the worst-case estimates. Shielding alone was not judged enough, so the orbit itself was shaped to dodge the worst of the belts. Juno flies a highly elongated path that swings in very close over Jupiter's poles and then back out to a great distance. The close approaches thread through a relatively narrow gap between the top of the atmosphere and the inner edge of the fiercest radiation, where the belts, which hug the magnetic equator, are thinnest. Most of each orbit is then spent far outside the belts entirely, out where the spacecraft can cool off, downlink its data, and prepare for the next dive. The trajectory is not a matter of convenience. It is a survival strategy written into the geometry of the mission, and it is why Juno loops over the poles rather than circling the equator the way most orbiters would. It helps to translate the doses into human terms. A whole body dose of a few hundred rads is enough to put a person in serious medical danger, and a dose several times higher is usually fatal. An astronaut somehow unshielded in the core of Jupiter's belts would reach that level in a matter of hours, not months. The problem gets worse the closer you go. Around the Moon, Europa, deeper into the system, the flux of high-energy electrons is roughly 10 times higher again, which is one reason any future lander there would face a hard clock. it would have only a limited window to work before the radiation degraded it beyond use. Jupiter does not just make missions difficult, it puts a time limit on them. The same calculus shapes missions still being flown. A spacecraft sent to study Europa, for instance, is far better off making dozens of quick flybys from a wide, safe orbit around Jupiter than settling into orbit around the Moon itself, because a tight Europa orbit sits inside the worst of the radiation and would use up the spacecraft in short order. So the mission becomes a series of brief passes, each one darting in, gathering data, and retreating to let the electronics recover. The radiation writes the flight plan, step back, and the pattern is unmistakable. We design our missions around Jupiter's violence. The amount of titanium, the placement of every circuit board, the shape of the orbit, the expected length of the mission, all of it is dictated by the radiation environment we have been describing. And there is a grim endpoint to it. Juno's mission has been planned from the start to finish with a deliberate plunge into Jupiter's atmosphere, partly to protect the moons from contamination, but also in frank acknowledgement that the accumulated radiation will eventually kill the spacecraft no matter what. And it is better to end on our terms than to leave a dead, uncontrolled object drifting through the system. That is the local thesis. Jupiter's hostility is not a turn of phrase. It sets the mass, the armor, the path, and the lifespan of everything we send, and it always wins in the end. On Earth, the aurora is a weather report on the Sunday. It brightens when a gust of solar wind or a magnetic storm slams into our magnetosphere, funneling charged particles down the field lines into the upper atmosphere near the poles, where they make the air glow. When the sun is quiet, the aurora fades and can vanish for nights on end. It is a visitor, and it comes and goes on the sun's schedule. Jupiter's aurora is a different kind of thing. It is the most powerful in the solar system, radiating on the order of hundreds of gigawatts, far more than Earth's, and where Earth's brightest displays last hours, Jupiter's run without stopping. Spacecraft and the Hubble Space Telescope have watched its poles for decades. The glowing ovals around them are a permanent fixture. They flicker, brighten, and throw off bursts. The reason is that Jupiter's aurora is powered mainly from within, and the dominant energy source is the planet's own rotation. Recall the picture from earlier. The fast-spinning magnetic field is trying to drag the heavy plasma of the Io torus around with it, once every 10 hours. Out beyond a certain distance, the field cannot quite keep that plasma rotating at full speed, and it begins to slip behind. That slippage sets up enormous electrical stresses in the system, effectively a planet-sized generator, and the currents it drives run along the magnetic field lines and slam particles down into the atmosphere near the poles, where they light the gas up. Io's volcanoes keep resupplying the plasma. The planet keeps spinning, and so the aurora keeps burning. The solar wind still modulates it, brightening some features and triggering others, but it is not the engine. The engine is inside Jupiter, seen in ultraviolet light, where spacecraft and Hubble study it best. Jupiter's aurora is not a single ring, but a structured system. There is a bright, fairly steady main oval, generated by the co-rotation breakdown just described. Inside it, closer to the pole, the emission is patchier and more variable, linked to processes further out in the magnetosphere. And outside it sit the small, sharp footprints of the moons, Io's the brightest, each marking where an electric current connecting that moon to the planet meets the atmosphere. Decades of Hubble campaigns have watched all of this flicker and rearrange, without the whole system ever going quiet. The glow is not only in visible and ultraviolet light, Jupiter's aurora also shines in X-rays. Something Earth's aurora does not do at all. And at Jupiter's poles, the X-ray emission has been seen to pulse with a regular beat, in some episodes brightening every few tens of minutes like a slow, planet-scale heartbeat. Producing X-rays at all requires particles. In this case, heavy ions. accelerated to far higher energies than a simple solar wind aurora ever reaches. It took decades, and several observatories working together to trace the pulses back to waves, rippling along Jupiter's magnetic field lines and periodically flinging ions into the atmosphere. The detail that matters here is the direction of the evidence. Everything about Jupiter's aurora points to a process being driven harder and more continuously than anything the Sun does to Earth. There is even a visible thread connecting the planet to its moons. Io leaves a distinct bright spot in Jupiter's aurora, linked to the planet by a current of charged particles flowing along the magnetic field. An electrical circuit tens of Jupiter's long joining moon and planet. Europa and Ganymede leave fainter footprints of their own, and Ganymede, uniquely among moons, even generates a small magnetic field and a faint aurora of its own. A magnetosphere nested inside Jupiter's. Each of these is a place where the machinery briefly becomes visible, so the aurora is not decoration on top of the planet. It is the visible discharge of the whole rotating, plasma-loaded engine lit from within. Where Earth's polar lights are, the Sun writing on our atmosphere, Jupiter's are the planet writing on its own. The sky above Jupiter's poles glows because of what Jupiter is doing to itself. Set a human baseline first. On Earth, a hurricane or typhoon runs for a few days, exceptionally a couple of weeks, before it moves over cooler water or land and unwinds. The longest-lived organized storm systems we know of persist for maybe a month. That is the scale our intuition is calibrated to. A big storm is a temporary event with a beginning, a middle, and an end that arrives fairly soon. Now look at Jupiter's Great Red Spot. It is an anticyclone, a high-pressure vortex turning counterclockwise in the southern hemisphere, and at present it is roughly the width of Earth, having been distinctly larger within living memory. Around its edge, the winds blow at something like 430 to 680 kilometers per hour, faster than any wind ever recorded on Earth. Where the fiercest tornado gusts top out well below that, the interior of the spot is comparatively calm. The violence is concentrated in a fast-moving collar around the rim, so the whole structure behaves like a slowly rotating island of high pressure with a racetrack around its coast. It is, by any reasonable definition, a storm, and it is a storm large enough to swallow our entire planet with room to spare. Here is the part that breaks the intuition. The Great Red Spot has been under continuous telescopic observation since 1831. Generations of astronomers have been born, trained their telescopes on it, published their drawings and measurements, and died. And the spot was there before each of them, and remained after. Nearly 2 centuries of unbroken watch, and it has never dissipated. It is not perfectly fixed. It drifts slowly in longitude, sliding around the planet relative to the clouds over years and decades, and its exact size and color vary. But the vortex itself has simply persisted. A single, coherent storm outliving everything and everyone that has recorded it. The history before 1831 is genuinely uncertain, and it is worth being careful about it rather than reaching for the most dramatic number. Between 1665 and 1713, Giovanni Cassini and others recorded a dark marking they called the permanent spot at roughly the same latitude as today's storm. For a long time, people took it for granted that this was the same feature, which would make the Great Red Spot well over 3 centuries old and possibly the longest-lived storm ever observed anywhere. But then the record goes quiet for more than 100 years, with no clear sightings, and recent modelling of how a vortex like this forms, drifts, and decays suggests the Cassini spot most likely dissipated, and that the storm we see now formed separately in the 18th or early 19th century. On top of that, the modern spot has measurably shrunk within the observational record. From a long oval, well over twice Earth's width in the late 1800s to the rounder, more compact form seen today, and its rotation and colour have shifted along the way. The colour that gives the spot its name is itself an unsolved problem, and it is a good example of how much remains open even here. The clouds elsewhere on Jupiter are mostly white and tan, tinted by ammonia, ice, and other compounds. The Great Red Spot's distinctive brick to orange hue is thought to come from chemicals dredged up from deeper levels and then altered by ultraviolet sunlight at the top of the vortex. Where the spot's high, slow rotating center pushes material up into the light. But exactly which chemicals, and why this storm reddens while others do not, is still debated, and the shade has visibly shifted over the decades. We can measure the storm to within a few kilometers and still not fully explain its color. Even the cautious reading leaves us with something extraordinary. A single storm, wider than Earth, that has held together for at least 190 years, and possibly much longer. That is the anomaly this part of the video has to account for. On Earth, a storm's lifetime is set by how long its local fuel lasts. On Jupiter, the Great Red Spot keeps a completely different clock. And the next chapter is about what wins that clock. The obvious guess about a storm that has lasted 2 centuries is that it must be deep, something that's stable, that resistant to being torn apart, surely reaches far down into the planet, anchored like the taproot of an old tree. It is a reasonable assumption, and for a long time nobody could test it, because from outside all you can see is the cloud top swirl. Juno tested it the same way it tested the jet streams, by weighing the storm. Any concentration of mass, including the denser or less dense air wrapped up in a giant vortex, tugs very slightly on a passing spacecraft and shifts its speed by a tiny amount. In 2021, mission scientists gathered a set of close passes, including 2 that flew almost directly over the Great Red Spot, and looked for that faint gravitational fingerprint. The result was a surprise, but in the opposite direction to the intuition. The Great Red Spot is shallow. Its roots reach only a few hundred kilometers below the cloud tops, with a firm upper limit somewhere around 500 kilometers, and a lower bound suggesting it does extend at least a couple of hundred kilometers down. Set against its width of a full Earth, it is a thin lens, vastly wider than it is deep, more like a coin lying flat than a column driven into the planet. Getting that number was not simple. The gravitational tug of the storm is a tiny fraction of Jupiter's total pull, so the team had to track Juno's velocity to within fractions of a millimeter per second, and then subtract, with great care, the far larger effects of the planet's overall shape and rotation. What was left, the faint residual signal as the spacecraft passed over the vortex, set the depth limit. What makes that result strange is the comparison with the flows around it. The east-west jet streams that border the Great Red Spot to the north and south, the currents that hem it into its fixed latitude band, run much deeper, down toward 3,000 kilometers, the same depth Juno found for Jupiter's jets in general. So the storm is a relatively shallow feature sitting inside a much deeper, more powerful system of currents. In effect, the Great Red Spot is a lens floating near the surface of a river system whose channels cut far deeper than the lens itself. That inversion is the key to the storm's longevity. The Great Red Spot does not survive because it is deeply anchored, the way we assumed. It survives because it is trapped and fed. The deep jets act like the banks of a river. Walls of fast-moving atmosphere immediately to the north and south, running in opposite directions, that pen the vortex into a narrow lane of latitude and keep it from drifting away, spreading out, or being torn apart by the surrounding flow. A vortex hemmed in like that is far more stable than one drifting free. And because those jets belong to the deep circulation, which is powered by Jupiter's internal heat, the storm sits in a channel that never stops being supplied with energy. Smaller storms that drift into the same latitude are frequently caught by the spot and absorbed, topping it up further, which is part of why its size can grow as well as shrink over the decades. So the local thesis is that the engine keeps the storm alive. The Great Red Spot is not a monument standing on its own foundations. It is a shallow eddy held in place by deep, permanent currents, drawing on the same internal power source as everything else on the planet. Its slow shrinking, then, is not the storm dying so much as the balance between it and its confining jets shifting over time. The vortex tightens rather than unravels. Take away Jupiter's internal heat, and the deep jets would slacken, the banks would erode, and a storm like this would lose its channel and spin down. Its centuries-long life is borrowed directly from the engine. For most of the space age, we had never properly seen Jupiter's poles. Spacecraft flew past near the equator, and from Earth, the planet is always presented more or less pole on edge. Juno's polar orbit changed that, and what it found at the top and bottom of the planet was not the formless churn you might expect at the ends of a chaotic world. It was geometry. At the North Pole, Juno saw a single cyclone sitting almost exactly on the pole, ringed by 8 more enormous cyclones arranged in a regular octagon around it. At the South Pole, the same basic design, but with 5 outer cyclones in a pentagon. Each of these storms is a rotating system, hundreds to a couple of thousand kilometers across. A continent-sized hurricane in its own right. And they are packed edge to edge like segments of a flower. What is remarkable is that they are stable. Year after year, orbit after orbit, the polygons have kept their shape and their spacing. The individual cyclones jostling against one another without merging into a single giant vortex and without flying apart. At one point, a 6th cyclone joined the southern group and then faded away again, and the 5-sided pattern reasserted itself. This is structure, actively maintained, at the poles of the most turbulent planet we know of. The lightning tells a similar story of familiar physics operating at Jovian scale. When Voyager 1 flew past in 1979, it detected radio crackles from Jupiter that were nicknamed whistlers because, slowed and spread out by their passage through the plasma around the planet, they sounded like a descending whistle. Whistlers are the fingerprint of lightning, so this was the first proof that Jupiter had storms with lightning at all. Juno, listening much closer with its radio and plasma instruments, recorded on the order of 1,600 lightning signals over about a year of close passes, and measured strike rates as high as roughly 4 per second in the most active regions. That is comparable to the rate in Earth's most vigorous thunderstorms, and several times higher than the peak Voyager had been able to catch from a single flyby. There is a twist. Jupiter's lightning clusters toward the poles rather than the equator, the reverse of the pattern on Earth, which is thought to reflect where moist convection can still punch upward on a planet whose equator receives a little more of the feeble sunlight. But the discharges themselves, stroke for stroke, look surprisingly Earth-like. Why the polar polygons hold together at all is still being worked out. The leading idea is that each cyclone is ringed by a band of the opposite kind of circulation, an anticyclonic shield that keeps its neighbors at arm's length, so the cluster settles into a spacing where every storm is held in balance by the others. It is a bit like coins pushed together on a table until they lock into a hexagonal pack, except the coins are hurricanes, and the packing is maintained by the flow itself. Whatever the exact mechanism, the point stands. This is not chaos that happens to look organized in a snapshot. It is a configuration that actively restores itself when disturbed. Juno's data also pointed to some genuinely new mechanisms, and these should be held as proposals rather than settled facts. The spacecraft found evidence of shallow lightning, discharges high in the atmosphere, in thin ammonia water clouds, and the team proposed that violent updrafts build slushy ammonia and water hailstones, nicknamed mush balls, that fall and carry ammonia down into the depths. It is a model that would explain why ammonia seems oddly depleted at certain levels, and it is still being tested. Set against Saturn, the contrast sharpens the point. Saturn also has a striking polar feature, but it is a single hexagonal jet stream, one big, 6-sided track. Jupiter's poles are different in kind. Not one geometric jet, but a tight cluster of discrete, coexisting cyclones. So the polygon is not a generic giant planet habit. It is something specific to Jupiter's conditions. The thesis for this chapter is that Jupiter's violence is patterned, not random. The storms obey geometry, the lightning obeys familiar rules, and that regularity is exactly what you would expect if a single underlying cause were organizing the whole system. The next chapter names that cause. We have now collected a long list of violent features. Internal heat that outshines the sunlight Jupiter receives, a circulation reaching 3,000 kilometers deep, the strongest magnetic field of any planet, a magnetosphere larger than the Sun, radiation belts that destroy spacecraft, an aurora that never switches off, and a storm wider than Earth that has lasted for centuries. The reasonable question at this point is whether these are separate facts that happen to co-occur on one planet, or whether they are one thing wearing many faces. Follow the heat and the storms back first. Jupiter's mass drives its slow gravitational contraction. That contraction releases heat from deep in the planet. The rising heat drives convection through a fluid envelope tens of thousands of kilometers deep, and the planet's fast rotation combs that convection into the deep jet streams. The jets, in turn, are the banks that trap and feed long-lived vortices like the Great Red Spot. And the polar cyclones are the same deep convection expressing itself at the top of the planet. Heat, jets, and storms are a single chain, and it starts with how much Jupiter weighs. That same mass raises the interior pressure high enough to turn a huge volume of hydrogen into a liquid metal. The same internal heat makes that metallic ocean convect, and the same fast rotation organizes the convection into a dynamo, which generates the record magnetic field. The field carves out the vast magnetosphere. The field forces Io's volcanic plasma to co-rotate, and the field then accelerates that plasma into the radiation belts and pours it into the poles as the permanent aurora. Field, magnetosphere, radiation, and aurora are a second chain, and it starts from the same two facts, the mass and the spin. Even Io belongs to the pattern. The moon erupts because Jupiter's gravity, working through an orbital resonance with the other moons, keeps flexing it. So the volcanic plumbing that feeds the plasma torus is itself powered by the planet's mass. The faint dust rings are debris knocked off small moons by impacts that Jupiter's gravity helped gather. Even the record-breaking number of moons is the same mass expressing itself as a reach long enough to have captured a swarm. Trace any thread far enough and it ends at the same place. So nothing on the list is a decoration added on top of a large planet. Each feature is a consequence of how massive Jupiter is and how fast it turns, routed through heat, fluid dynamics, and electromagnetism. Notice how few independent inputs there really are. Not a dozen separate causes, but essentially two numbers, the mass and the rotation rate. Feed those two into the physics of a hydrogen-helium body and the internal heat. The deep jets, the metallic ocean, the dynamo, the field, the magnetosphere, the belts, the aurora, and the long-lived storms all fall out as consequences. The planet is elaborate on the surface and simple at its root. You can see this by running the counterfactual. A hypothetical Jupiter of half the mass would contract less and generate less internal heat, so its deep convection would be weaker. Lower interior pressure would metallize less hydrogen, so its dynamo and its field would be weaker, and its radiation belts far softer. Weaker jets would give a storm like the Great Red Spot shallower, leakier banks, and it would spin down, reduce the mass, and the violence recedes across the board. In lockstep, that is the thesis that carries into the final section of the video. Biggest and most violent are not two independent claims about Jupiter that we have to reconcile. They are the same property. Mass, described once through geometry and once through behavior. What remains is to say precisely what kind of object that makes Jupiter, and that means going back to the line between a planet and a star. The single most common thing people say about Jupiter, after "it's the biggest," is that it is a failed star, a would-be sun that didn't quite make it. It is a memorable phrase, and in its usual meaning, it is wrong. It is worth taking the time to say exactly why, because the correction is what lets us name what Jupiter actually is. Start with the thresholds, which we met briefly at the beginning and can now use properly. To sustain the ordinary hydrogen fusion that powers the Sun and keeps a star shining for billions of years, an object needs roughly 75 to 80 times the mass of Jupiter. There is a lower, gentler bar as well. An object of about 13 Jupiter masses or more can fuse deuterium, a heavy form of hydrogen, for a while. That deuterium-burning line is the conventional boundary between a planet and a brown dwarf. Jupiter has 1 Jupiter mass. It does not sit just below the fusion line. It sits an order of magnitude below even the lower one. It is worth being clear about how modest deuterium fusion actually is. An object above about 13 Jupiter masses can fuse deuterium, but deuterium is rare, only a trace of the hydrogen present, so it burns out in a geologically short time and then the object simply cools for the rest of its existence. That is why brown dwarfs are sometimes called failed stars, with more justification than Jupiter ever earns. They do ignite, briefly, and then fade. Jupiter never ignites anything. Its center is hot, tens of thousands of degrees, but that is compression heat, not fusion heat, and there is a categorical difference between the two. So the reversal is this: Jupiter is not a star that fell short by a whisker. It is the largest object its formation process was capable of building out of the gas and ice in the disk around the young Sunday. A giant planet grows by first assembling a core and then pulling in surrounding gas, and that process becomes self-limiting. Once a planet is massive enough, it clears a gap in the disk around its orbit and cuts off its own supply. Models suggest this route tops out somewhere around 10 Jupiter masses at the very most, and usually well below that. There is a real gap, several Jupiter masses wide, between the heaviest planet that can form this way and the lightest object that can fuse deuterium. Jupiter sits comfortably on the planet side of that gap, near the ceiling of its own category, not scraping the floor of the stellar one. That ceiling is a real, physical thing, and we can state the mechanism cleanly now. For a cold body made mostly of hydrogen and helium, there is a particular mass, and it happens to lie near Jupiter's, at which the object reaches its maximum possible radius. Below that mass, adding material mostly adds volume, and the body grows. Above it, the situation flips. The extra gravity from any new material compresses the interior more than the material itself, adds to the outside, so the body gets denser and its center gets hotter, while its diameter barely changes, or even shrinks. Push far enough up in mass and you reach brown dwarfs and small stars, some of which are physically smaller across than Jupiter despite weighing tens of times more. Jupiter is close to the widest a cold ball of this composition is ever going to be, which is a strange kind of record. Not the biggest possible object, but the biggest possible planet. We can see this ceiling directly in other star systems. Astronomers have found many giant exoplanets of 2, 3, 5 Jupiter masses that turn out to be only marginally larger than Jupiter across, exactly as the compression argument predicts. So Jupiter is a planet sitting at its physical maximum size. That is precisely why its internal engine runs so hard. It is a body carrying the largest gravitational load a planet can carry. And the next chapter puts a name to what that makes it. If Jupiter is not a failed star, and not simply a scaled-up Earth, then what is the right way to think about it? The answer this video has been building toward is that Jupiter is best understood as a self-powered engine that happens to be shaped like a planet. Take the scaled-up Earth idea apart first. On Earth, essentially everything that moves in the air and ocean is driven by the Sunday sunlight heats the tropics more than the poles. That imbalance drives the winds and currents, and the weather is the result. Take the sun away and Earth's atmosphere would go still and freeze. Almost nothing about Jupiter's activity works like that. The sun's light at Jupiter's distance is a few percent as strong as at Earth, and it barely reaches below the cloud tops. The planet's heat, its winds, its magnetism, and its radiation are, to first approximation, its own. Now list what it runs on. It releases heat left over from its own formation and from its slow, ongoing contraction at a rate somewhere between 1.5 and 2 times everything it absorbs from the Sunday. It runs a dynamo in a deep ocean of metallic hydrogen, generating a magnetic field with a strength around 20 times. Earth's at the cloud tops and an overall magnetic moment some 20,000 times greater. It inflates a magnetosphere larger than the Sun and drives the most powerful aurora in the solar system, hundreds of gigawatts, from its own rotation. Every one of those has an internal power source: gravity and contraction for the heat, rotation and metallic hydrogen for the field and Io's volcanoes for the radiation belts, and the polar lights. There is no step anywhere in that chain where you have to point at the Sunday. Remove the Sun entirely, and Jupiter would go on generating heat, spinning up a field and lighting its poles for billions of years, barely noticing. That is what justifies a change of category. Jupiter is not a large version of a rocky planet with the Sun turned down. It is a body that generates its own heat, its own magnetism, and its own light shows. Sitting at the maximum size a planet of its composition can reach. The word that fits is engine. A system that takes a stored energy supply, in this case, the gravitational energy of its own assembly, and converts it, without pause, into motion, heat, and electromagnetic power. It is not a violent engine because something is wrong with it. Violence is what the engine produces when it is working normally, the way an idling turbine is still deafening up close. The scale of the throughput is worth holding in mind. The power leaving Jupiter's interior is not a rounding error on the sunlight it receives. It is comparable to the entire solar input, radiated steadily for billions of years. That is still nothing like a star. The Sun outshines Jupiter's internal output by a factor of billions. But it is a genuine, self-sustaining power plant, and it is the largest one any planet runs. Everything downstream, the jets, the dynamo, the belts, the aurora, is that power plant's exhaust, routed through fluid dynamics and electromagnetism into the forms we can see and measure. This reframing also explains why exploring Jupiter is so unlike exploring anywhere else. You do not send a probe to observe a planet sitting quietly in sunlight. You send it into the working parts of a running machine, and you build the probe to survive being inside a machine. The titanium vault, the belt-dodging orbit, the flybys instead of orbits, the planned death in the atmosphere, all of it follows from the fact that the object under study is generating its own hostile environment, and will keep generating it no matter what we do, or whether we are there at all. And here is the peak of the reclassification, what we have been calling Jupiter's violence, the belts, the centuries-old storm, the aurora that never rests, is simply this engine running at its normal output. It is not a phase, not a crisis, not a run of bad luck. It is the idle state. The engine has been turning over like this for longer than Earth has had a solid surface. And it will keep going, gradually winding down for tens of billions of years, far longer than the Sun will last in its present form. Jupiter is violent for the same reason it is large, because it is a maximum mass planet, slowly burning the energy of its own gravity. And that is just what such an object does. So far, the violence has all pointed inward or stayed local to the planet. But an engine with Jupiter's mass also reaches out, and its gravity acts on everything that passes through the outer solar system. The clearest demonstration came in July 1994. A comet designated Shoemaker-Levy 9 had been captured by Jupiter years earlier into a loose orbit, and on a close pass the planet's tides tore it into a train of more than 20 fragments. Those fragments came back around and struck Jupiter one after another over the course of a week. Each major impact left a dark scar in the clouds. some of them as large across as Earth, and the marks were still visible for months. The energy delivered by the largest fragments far exceeded the entire nuclear arsenal of the world, and it was the first time humanity watched a planetary-scale collision happen live. That was a spectacular one-off, but smaller hits are routine. Since 2010, amateur astronomers watching Jupiter through backyard telescopes, along with professional surveys, have caught brief flashes in its atmosphere, each lasting a second or two, roughly once every 1 to 2 years. An amateur was also the first to spot the scar from a 2009 impact, before any observatory noticed it. These are not comets kilometres wide. They are objects ranging from a few meters to tens of meters across, the kind of thing that would produce a bright fireball or a modest airburst at Earth. The frequency contrast is the point. Jupiter is struck by these small bodies far more often than the inner planets are, and not only because it presents a bigger target, its enormous mass focuses their trajectories, bending nearby paths toward itself and pulling in material that would otherwise have drifted past. It also holds a huge population of small bodies in its own vicinity, from the Trojan asteroids that share its orbit to a family of short-period comets it has captured and reshaped over time, and some of those eventually fall in. A giant planet acts as a gravitational funnel, and Jupiter is the largest funnel in the solar system after the Sunday. Whether that funnel is, on balance, good or bad, for Earth is a genuinely open question, and it is worth being honest that the science is unsettled. The popular story casts Jupiter as a shield, a cosmic vacuum cleaner that clears out comets and asteroids that might otherwise reach us. That idea has real support, going back to simulations from the 1990s. But other simulations push back, suggesting Jupiter also deflects some objects inward or stirs up distant reservoirs of comets, and that the net effect on Earth's impact rate might be close to a wash or even slightly negative. Different studies reach different answers depending on which population of impactors they track. The same sweeping shows up as debris close to home. In 1979, Voyager 1 discovered that Jupiter has rings of its own, far too faint to see from Earth in ordinary light. Fine dust, kept aloft in thin sheets, continually replenished by micrometeorites blasting material off 4 small inner moons. Those rings are, in a sense, the visible residue of the same process. Small bodies drawn in by Jupiter's gravity and ground to powder against its satellites. Jupiter's reach also helped shape the solar system we live in. Its gravity is a major reason the asteroid belt never assembled into a planet, stirring those orbits so the material there stayed as rubble. It is thought to have influenced how much water and volatile material was delivered to the young inner planets, and it anchors the Trojan swarms of asteroids that ride 60 degrees ahead of and behind it in its own orbit. The details of that early history are still debated, but the scale of the influence is not. What is not in doubt is the reach itself. Jupiter's gravity measurably shapes the orbits of comets, asteroids, and its own swarm of Trojan companions, and it can capture a passing comet for years, as it did with Shoemaker-Levy 9, before either flinging it away or drawing it in. The same mass that makes the planet violent also makes it the dominant gravitational actor among the planets. That reach is the last outward-facing piece. The final question is what all of this says about the planet's interior, and what the whole picture adds up to. There is one more picture to let go of before we close, and it is the one most of us grew up with. The standard textbook diagram of Jupiter shows a small, dense core of rock and ice at the center, wrapped in a thick shell of metallic hydrogen, wrapped in turn in the outer layer of ordinary hydrogen and helium, a stone heart inside a gas giant. It is tidy, and Juno's measurements have made it hard to sustain. The evidence again comes from gravity. As Juno skims low over the planet, the precise pattern of its acceleration encodes how mass is distributed inside, and in particular, how much is concentrated toward the center. When the mission team fitted interior models to that pattern, the versions that worked best did not have a compact core with a sharp edge. Instead, the heavy elements, the rock and ice, appeared to be spread out, blended into the surrounding hydrogen over a large fraction of the planet's radius, by some estimates close to half of it. Planetary scientists call this a dilute or fuzzy core, not a distinct body you could point to, but a gradual enrichment, densest at the very center, and thinning outward with no clean boundary where core stops and mantle begins. It is important to be careful about what kind of result this is. Nobody has seen Jupiter's core. This is an inference from gravity measurements combined with models of how hydrogen and helium behave at millions of atmospheres of pressure, and those models carry uncertainty. Alternative interior structures are still discussed, but the neat, sharply bounded rock core that the old diagrams show is no longer the best fit to the data. And any correct picture of Jupiter's inside now has to account for a center that is smeared rather than solid. The dilute core also feeds back into the story of the internal heat. If heavy material is mixed through a large volume rather than settled into a tidy center, then the slow, ongoing separation of that material, heavier stuff gradually sinking, lighter stuff rising, is itself a source of energy, on top of the plane contraction we discussed earlier. A fuzzy core is not just a structural curiosity. It is potentially part of what keeps the furnace stoked. Alongside that, a smaller piece of texture. Jupiter also holds more moons than any other planet, well over 90 confirmed, and the count still creeping upward as surveys find more small, distant ones. The overwhelming majority are irregular chunks a few kilometers wide, captured asteroids and comet fragments. Only the 4 large Galilean moons carry any significant mass. It is another expression of the same gravitational dominance. A planet massive enough to have gathered an entire swarm and hold it. There are 2 broad ways to get a fuzzy core. One is that it was never fully compact. As Jupiter formed, heavy material and gas may have kept mixing, so a sharp core never had a chance to settle out. The other is more dramatic. Some models propose a head-on collision, early in Jupiter's history, with a protoplanet perhaps 10 times the mass of Earth, an impact energetic enough to blast into the center and stir a once solid core up into the surrounding hydrogen, from where it never fully resettled. Both ideas are unproven and hard to test, but it is a fitting uncertainty to end on. A planet whose very center may have been smeared out by the same kind of violence it now visits on everything that comes near it. The landing thesis for this section is that Jupiter is engine, not onion. From the dilute core through the metallic ocean, the convecting envelope, the deep jets, and out to the radiation belts and the aurora, it is better read as one graded, active, self-powered system than as a set of quiet layers wrapped around a stone. There is no clean center to point to, and, it turns out, no clean edge either. The planet fades into its magnetosphere, the way the core fades into the mantle. Here is the test that pulls the whole argument together. Imagine we could rebuild Jupiter at a fraction of its mass, say a third or a half, keeping the same hydrogen and helium recipe and the same orbit at 5 times Earth's distance from the Sunday. Which of its violent traits would survive the shrink? Start with the heat. A less massive planet exerts less gravitational squeeze on itself, so its slow contraction releases proportionally less energy. The internal heat flux would drop, and with it the strength of the deep convection that carries that heat outward. The engine's power supply would be turned down at the source. We do not have to imagine this from scratch, either. Neptune and Uranus are the small end of the same family, still emitting some internal heat, still banded, but with weaker circulations and nothing remotely like Jupiter's storms. A half-mass Jupiter would sit somewhere between them and the planet we actually have. Follow that through to the field. Lower mass means lower interior pressure, and lower pressure means a smaller volume of hydrogen gets squeezed into its metallic, electrically conducting state. A thinner shell of conductor, stirred by weaker convection, makes a weaker dynamo. The magnetic field would be a fraction of its current strength, closer to the modest fields of the ice giants than to the record-setter Jupiter actually has. The magnetosphere would shrink toward the planet, its tail no longer reaching anywhere near Saturn, and the radiation belts, which need a strong field to trap particles and a fast spin to accelerate them, would be far milder. A smaller Jupiter would not need a spacecraft to carry a titanium vault. It would not be a spacecraft killer at all. Now the storms. Weaker internal heat means shallower, slower jet streams, because the heat rising from within is what drives them. The deep, fast currents that currently act as riverbanks for the Great Red Spot would be feebler and less able to pen a giant vortex into a fixed latitude or keep pumping energy into it. A storm the width of Earth needs both a stable channel and a constant energy supply to survive for centuries. Take away either and it unwinds. On a half-mass Jupiter, a Great Red Spot might still form now and then, but it would leak, drift, and spin down over years rather than lasting through 200 years of telescopes. The polar cyclones would be looser, fewer, and more prone to merging or scattering. Put it together, and the conclusion is hard to avoid. Strip mass away from Jupiter, and its violence recedes across every category at once. The heat, the field, the radiation, the storms, all fading together because they were never separate properties to begin with. They are all outputs of the same gravitational engine, and the engine's power is set by the mass. You cannot dial down one without dialing down the rest. Run the experiment the other way, adding mass instead, and the opposite happens in the same coordinated way. A heavier Jupiter contracts harder and runs hotter. Metallus is more hydrogen and drives a stronger dynamo, traps harsher radiation, and holds its storms in deeper, faster channels. Curiously, it would not get much wider. The extra mass would go into compression and heat, not diameter, so you would end up with a body much like Jupiter to look at, but fiercer in every way that matters. Keep adding mass, and, somewhere past roughly 13 times Jupiter's mass, deuterium fusion flickers on in the core, and the object is no longer a planet at all. In other words, Jupiter is already close to the most violent a planet can be, because a more violent version would have crossed the line into being a brown dwarf. That frames the answer to the title as sharply as the evidence allows. Jupiter is the most violent planet because it is the most massive one, and it sits about as high on both scales as the definition of planet permits. The title is not describing a coincidence. It is describing a limit. Go back to where we started. On a clear night, with a modest telescope in a backyard, you can find Jupiter as a small pale disk, with a few faint stripes across it. And if the air is steady, you will notice that the disk is not quite a circle. It is slightly wider than it is tall, a little squashed. That is the ordinary view, the one available to anyone, and it is where this began. It is very close to what Galileo saw in 1610, when he turned one of the first telescopes on Jupiter and found a small disk flanked by 4 points of light that shifted position from night to night. Those points were the large moons, and noticing that they circled Jupiter rather than Earth was part of what broke the old picture of the cosmos. 4 centuries later, the disk between them has broken another picture. It is not a scaled-up world. Now, the same image reads differently. That flattening is the planet's 10-hour spin, fast enough to throw its own equator outward by 4,000 kilometres. The stripes are the tops of jet streams that run 3,000 kilometres deep, combed into bands by that same rotation. The faint warmth the planet radiates, invisible in the eyepiece, is mostly its own. The leftover heat of a body still slowly contracting under 318 Earths of gravity. Every part of what you are looking at is the surface of an engine. So the reclassification, stated once, plainly, Jupiter is not the solar system's largest planet, and, as a separate matter, its most violent. It is a body for which being that massive and being that violent are the same physical fact. Seen from two sides, the mass sets the internal heat. The heat and the spin build the storms and the dynamo. The dynamo builds the field, and the field builds the radiation and the light. Take away the mass and all of it fades together. Add mass and it all intensifies together until the object stops being a planet. Jupiter is not near that edge by accident. It is near it because it is the largest a planet is allowed to be, and it is as violent as that limit permits. And the part in the eyepiece is only the calm center of it. The planet's true extent is not the striped disk at all, but an invisible magnetic bubble larger than the sun, breathing in and out with the solar wind, with a tail streaming away to the orbit of Saturn. It is filled with plasma, stripped a ton per second from a burning moon, wrapped in radiation belts that would kill an unshielded traveler in hours, and lit at both poles by an aurora that has never once, in all the time we have watched, gone dark. If that bubble glowed, it would hang in our sky wider than the full moon. That engine was already running long before there was anyone to look at it. It was turning over when Earth's surface was still molten. It was turning over when Galileo first resolved it into a disk. It is turning over now while you hold a telescope on it, and it will still be turning, slowly winding down, tens of billions of years from now, long after the sun has changed beyond recognition. The biggest planet is the most violent planet, because the two were never really different things. The internal heat, the record field, the belts that kill spacecraft, the storm older than the telescope that found it. Run each of them back and they arrive at the same fact. A great deal of mass, held under its own gravity, doing what a great deal of mass does. Everything else is that fact, seen from a different angle.